Okay, so this week we're going to be looking at SNMP, which is quite a small area of Chapter 5. I've split Chapter 5 into two. So last week we did the first half of Chapter 5, along with access control lists, which was Chapter 4. This week we're going to do Chapter 5, which is quite the other half of Chapter 5, which is quite small, and Chapter 6. Now, what we're going to be looking at is SNMP. Now, SNMP might come up in your multiple choice assessment. However, it won't come up in the practical assessment because you can't perform SNMP commands on the packet tracer. So it was one of the things that had to fall by the wayside. So in terms of the commands and, you know, that kind of thing, in a practical sense, it's okay. You don't need to you know, learn them parrot fashion. However, just bear in mind that you may be asked questions on SNMP, including how you configure it. So don't ignore it in terms of your revision for the multiple choice theory exam, but know when you come to do the practical that this won't form part of the practical at all. Alrighty. So SNMP, what is it? Simple Network Management Protocol. What it allows you to do is it allows an administrator to monitor and manage different network nodes. So they can sit in one area and they can be getting fed information from different network nodes about what's happening on the network, just so you've got a picture of the network. You can have different front-end interfaces. I mean, it basically just chucks data back up. And obviously you need a nice front end on it, a nice interface to even have a pictorial diagram of your network, and you can see maybe if something's getting congested, it'll flash up red or something, or, you know, or if a node goes down, it can flash or something like that. So definitely using a front end makes it a lot more usable experience than just simply using it on a router. So you do need some kind of fancy front end for it. So basically, how it collects the data, you've got an SNMP manager, and that collects information from the agent. Now, the agent might be a managed node, like a switch. It might be a router. It could be a firewall device. You know, just any different sort of networking device that can send data. You know, you can set it to send data back up to the SNMP manager. There's also what's called a management information base, and that's just like a database. It holds all the data that's been sent to it from all the SNMP agents, and that's what a front end would use. It would use that database to give you a nice pictorial diagram of what's going on your network. So the SNMP manager, it can get information from agents by using a get action. It can also change configurations. So depending on what is happening on that node, it could be that, you know, that there is maybe congestion or an interface has gone down, or you want to try and implement load balance, or, you know, it could be something going on, but you can change configurations using the set action. And you can also set traps, and traps are not, it's not something to fall into. A trap is like, if you reach a certain threshold, then it'll flag something. So you don't need to constantly monitor it. It will monitor it and it'll say, right, okay, if it goes above 100 megabits per second, then I'll say, you know, that's fallen into that trap, or it's caught in the trap, and it'll flag it. So it's just a way of basically being able to monitor and manage your network remotely and get information about what's going on in your network. Jamie, I'll have a wee look at your question just in a minute, just once we've finished, because I can't see it that small. So SNMP agents that reside on managed devices, so it could be like the routers, the switches, the firewalls, etc. They collect and store information about the device. It's stored locally on the switch or the router or the firewall or whatever device it is in what's called the management information base. the SNMP manager then uses the SNMP agent to access the information that's in the locally held information base and pulls it back to a central place. There are GET requests, and an SNMP GET is obviously a request to ask for data back. And you can see some of the requests up in the top right here. A GET request retrieves a value from a specific variable. GET next request retrieves a value from a variable within a table.
Say, Ian, we're not getting any screens. We've got you on the screen.
Oh. There we go. That should be better now. I'll quickly flick back to that previous slide then, just to show you that overview. So the SNMP manager is the central point. So that would be like a network admin that would be sitting here. And he's just basically collating information from the different SNMP agents. And like I say, they can be routers, they can be switches, they can be firewalls that are all providing information back to the SNMP manager to give you a flavour of what's going on in your network. It's a two-way street. You can get information, but you can also set information. You can set things dependent on what's happening. So it isn't just purely a read kind of process. SNMP has got a two-way kind of process about it. So yeah, up in the top right here, you should be able to see it now. Thanks for that. There's different commands now. You won't have to know these commands for the practical, but you might be asked about some of them for the theory. So just to get an idea, GET request gets a value from a specific variable that's stored on the database, that's or the management information base, like a database, on the router. GET next request requests a value from a variable. Get a bulk request, obviously it gets a large block of data, such as multiple rows in a table. And that only works with SNMP v2 or later. And we'll look at the different versions of SNMP in a minute. A GET response replies to a GET request, GET next request, and a set request. And a set request is obviously stores a value in a variable. So basically the SNMP manager is, if you think about that, that is a machine or a computer at a network administrator's end that is pulling all this information together. And they can go and get information based on, you know, the different information that's held on different routers and switches and so on. But it is all about, if you think about what SNMP is, it's all about getting information about your network and about how efficient it's running and if there are any problems or any errors occurring. And it allows you to look at that and see it in real time and do things about it. So, like I was saying, a network management system, which is the kind of fancy front end, if you like, periodically will poll the SNMP agents using the GET request. And using that process, the SNMP process can collect lots of information, monitor traffic loads, verify device configurations are what they should be, alter them if need be. The agents are the ones that generate and send traps of information to the network management system immediately based on certain events. So remember, a trap is not something to try and trap something or someone into. A trap is just like a threshold. Once a threshold has been reached, it pings back a message to say that threshold's been kind of reached. So don't think a trap, you know, it's something like network management to try and trap people into. It's not that. It's if you've reached a certain threshold, that if your input queue is starting to get full and you're going to start getting congestion on the line, then maybe once you get to 80%, then a trap will be set at 80%. And if you reach that 80% threshold, then a message will go back and you've got time to then do something about the impending congestion that's about to happen. So It's very clever. It's very clever and lets you see exactly what's going on in your network and hopefully do something about it before you've got a problem. But hopefully 99% of the time your network's running fine and everything looks hunky-dory. But you sometimes see in large networks, you might have a huge big TV in a room somewhere and it's got a pictorial diagram or representation of the network and it's all in real time. And that information that's showing about how well the network's running is coming from SNMP. So there are different SNMP versions, obviously, as things have gone on, become more complex. There are different versions. SNMP 1 uses a community string match for authentication. It's okay, but it's not very secure. Again, version 2, there was some of the things that we could do, you could only do in version 2. So version 2, or specifically version 2C, again, there's no encryption, and it uses a community string match for authentication. So it's a bit like, if the word on the database matches the word, or the word on the agent matches the word on the management information base, as long as you've got that, there's a little bit of kind of authentication there, but it's not great. It's not very secure. So all versions, it says use SNMP managers, agents, and MIBs. This course focuses on versions 2C and 3. So you wouldn't be looking at version 1 anymore. 2C obviously uses a community string, not great, no encryption. Version 3, you've got different versions of that. So version 3, you've got no authentication, no privacy level. That uses a username, no encryption. It uses a username match for authentication, a slight improvement over version 2C, still not great. You've got authorization with no privacy, so you've got MD5, secure hash, and it provides authentication. But again, there's no privacy, there's no data encryption actually happening on the actual data itself. And then there's SNMP, the level auth priv. You've got to have a software image that can take it. So your iOS version has to be of a certain level that allows cryptographic encryption. If it does, then you can use DES or AES, and you've got MD5 or SHA for your authentication. It provides secure authentication, secure encryption. So all the information that's flying about your network is all purely authenticated and purely encrypted, which is probably the level of security that you would want to put in. Yes, it's going to be much more complex and much more difficult to set up initially, but you've got that offset that it's much, much more secure. You wouldn't want somebody being able to just plug into your network and start hacking your SNMP, because that could cause utter chaos on your network. So a network administrator must configure their SNMP agent to use the SNMP version supported by the management station. So makes sense. But you'd probably be, if you were looking for the best, the auth priv with the secure authentication, secure encryption, is definitely the one. So community strings, that is just a pure match with, does the community string belong to the same community? And that's really for, to ensure that you're getting SMP requests from the area that you want. There's nothing really about security in there at all. So it says, does my community string match to hash B7 exclamation 9 question mark? Yes. Is 192.168.1.5 an IP address? I know. Yes. And then obviously you can see here, so somebody's trying to get information, and that's verifying the community string and the IP address. And the web server with the SNMP agent says, okay, yeah, I can trust him. I know the community string. I know that's an IP address I can trust. Boom, I can give you the information. So there's read-only community strings. that provide access to the variables, but no changes can be made. And there's read-write access as well, just a bit like file folder structure. Provides read and write access to all objects in the MIB, so you can overwrite things. So once you get into the nitty-gritty of it, basically the management information base, each variable has got an object ID, and if you think about a database, it's the same kind of thing as a database. Each database entry will have a unique entry, against it. So it's a similar kind of thing. That's the way I always try to remember it, was to think about SNMP management information base as being like a database, and the word base helps you to remember that. So OIDs uniquely identify managed objects. They're based on the RFC standards. It's a hierarchy or tree. Vendors such as Cisco have got their own private branches, and that allows them to create their own variables. You can see ISO, Organisation, Department of Defence, Internet, Private, Enterprises, and then Cisco have got their own. So they've got their own object ID. CPU is one of the key resources that should be measured continuously for a networking device. And an SNMP graphing tool, that's what I was saying, the front end visuals of this can periodically poll SNMP agents and graph all the values, so you can see all of this information at a glance without having to go in and question it and go, what? Okay, so it's what? You need all this info because there's loads of information getting pulled from everywhere, so you need to be able to see it interactively, and that's why you need some kind of front end, like I say, to pull all this data together. So SNMP version 3, remember the secure one, it can authenticate and encrypt packets over the network, and it provides secure access to devices. Because remember, you're not only reading the information from these devices, you can write to them as well. And you wouldn't want everybody or anybody being able to write to and manage your managed nodes. So you want it to be secure. So message integrity and authentications, transmissions can be authenticated, they can be encrypted to ensure privacy, and the access control can restrict SNMP managers to certain actions. So certain people can do certain things, and maybe only one person can do everything, and other people can only do certain things. Just so you've got, different managers can do certain actions. There is a lab based on this that you can have a wee look at. It's basically doing a bit of survey and a bit of research and looking at network monitoring tools. But it's worth having a wee look at just to see what the network monitoring software looks like. Because obviously they base, what the visuals they're showing you from the SNMP information. So, like I say, you're not going to be doing this for the practical. You might need to know some of these things in terms of the multiple choice. I'm not really sure. But certainly if you wanted to set up an SNMP server, basically configure the community string. So we're talking at basic level, obviously. Configure the community string and the access level using the SNMP server community. And they've called their community baton.org or something. They've made it read-only. So it can be read-only or read-write. And they've got an SNMP ACL, obviously, to configure access to that. They've got an optional location, so you can see where this is located. Obviously, that's just a text kind of thing, just to say it's a text command. Again, the contact is optional. So who do you contact if you need to get information about the SNMP server? They said Wayne World, very original. Again, all of these are optional. They have said that there is a host 192.168.1.3 version 2C, so using version 2C, for that community string, and the server is going to be 192.168.1.3, it looks like, which is here. Yeah, that's SNMP server. They're going to enable traps at some point, so obviously there's going to be some traps to set different thresholds, and there is going to be, there's the access control list it's referring to. So there's an IP access list standard, SNMP, ACL, and it's permitting 192.168.1.3. So it's only allowing that one device to be able to, view and use SNMP information, which is sensible. How do you verify it? Once you put those commands in, show SNMP, and you can see all of the information comes up. And it says Kiwi syslog server is one of the several solutions that display SNMP output. There are other ones, obviously. The SNMP traps are sent to the SNMP manager. They're displayed on the syslog server. To verify, you just do show SNMP. And you can do show SNMP community to show the community string and the related ACL information that's tying that up. Best practice, because SNMP can create security vulnerabilities, if you're using SNMP v1 and you're worried about security vulnerabilities, don't use it. If you're using v2c, again, if security vulnerabilities are worrying you, probably you're best to use some form of v3. But if you've got to use v2 for whatever reason, make sure your community string is really strong, hard to guess. Change it frequently. Use an ACL to prevent SNMP messages from going beyond the required devices that you need it to. And so you've got a little bit of security around, only the person with that ACL or the machine that belongs to the permitted statement on the ACL gets access. But it says SNMP is recommended because you've got that authentication, you've got the encryption. So the SNMP server group, we either say v1, v2c, or v3, and you either give it auth, no auth, or priv. So you want auth and priv to be on for the best security. SNMP server user, username, group name, used to add a new user to the group, so you can add more people in. So here, what you would do for SNMP v3, you would set your access list, you would permit whoever you need to permit, and you set up your permissions first. You would configure your SNMP server, give it a view, configure an SNMP group, and then remember v3, whether you want the privacy and the authentication, do you want read access, or do you want, write access, and then add your user, configure a user as a member. Okay, and you've obviously got your different authentication standards, put in the password and your privacy standards in there as well. So you can use MD5 or SHA, or you can use DES, triple DES, AES, and either 128, 192, or 256 security. So you've got it really, really secure. So here it is on the router. The example there shows an ACL. It's named permit admin. It's configured to only allow 192.168 1.0/24 network. All hosts attached to the network will be allowed to access SNMP agent, which is running on router 1. And an SNMP view is named SNMP RO, which is read-only, and is configured to include the entire ISO tree from the MIB. And the ISO tree, I think, was the it's number 1 there. So IP access list standard permit admin, you're permitting the full network, then you exit, then you go into server view, SNMP RO, and you say ISO, and that's included in the view. You then give a group admin, and then you set up your privacy, and then you're saying permit admin is who you're allowed to access, and then you're allowing a user, so the user's Bob admin. It's going to be using version 3 with authentication with SHA, and it's Cisco 12345's password and privacy. AES 128 security with Cisco 54321 is the password, and that's it. So not a lot of commands to really get it up and running. There is a lab, like I say, unless you've got the physical equipment, you can try and put the commands in. Yeah, they're just not there on Packet Tracer, which is unfortunate. If you have got real kit to play with, you can do that. Or if you've got JNS3, you can play with that as well. Okay. Before I move on and go on to quality of service, how was that for SNMP? Just knowing that you only need to know the theory about it. You don't need to know the practical element, and you don't need to know how to set it up. But from the theory side, basically remember, it's just it's a way of getting information to a central point about what's going on in your network. You can set it up on routers, switches, firewalls, any Cisco device. You pull it back to a main server. Then you use some piece of software that will be able to interpret that information that you're getting and show you in a more graphical or pictorial way. But is that okay for SNMP? Does anybody want to ask anything before we move on to quality of service? Just while you're thinking about it, I'll look at Jamie's question. I'll just see if that's the right one. I'll just need to double click the picture because I can't see it. No, not quite. No, that's not the two. I'll just type it. Okay, I was just typing up there, just to make it clear. So from the Cisco chapters, so from the Cisco curriculum, you need to obviously do the chapter exams 1 to 6. So finish chapters 1, chapters 2, 3, 4, 5, and 6. Then there's a practice final just to prepare you for the final, which we'll be looking at probably next week. I think once I do a summary, you'll be able to do that at some point next week. Then the week after, we'll be probably looking to do the final. Any last revision around, you know, how, depending on how people did on the practice final. Then we'll do the final. And then we're looking at probably a reset week near the end. And we'll also go over the revision for the practical as well. We'll probably do a couple of wee sessions around that. Okay, is everybody okay if we move on to quality of service then? Okay. So quality of service, basically, right, but just before I start, I'll have a quick look at this one. Yeah, that's it, final exam, yeah, that's the one. Yeah, so yeah, I haven't made it available. You still need to do the course feedback first. So you do the course feedback, then you do the final exam. Course feedback is just the survey thing. Yeah, that's the one. That's the one. So quality of service then. Quality of service has come about because certain packets are time sensitive and certain packets are not time sensitive. And the way that networks have changed over the last 10 years even, things have changed a lot in terms of how we use network packets, what we use them for. I mean, can you think 10 years ago that you'd be streaming things, to your TV with the quality that you've got? It just, I mean, I can remember watching like these streams that you would get of the football 10 years ago, and it was like you could see a green screen and maybe like wee matchstick kind of things moving about. You had no idea what was going on. That was really before quality of service became a thing. So there are some types of traffic that require much greater resources, so they need much bigger bandwidth from the network than some other kinds of traffic. So the kinds of traffic we're talking about are kinds of traffic. What's the minimum past the practice final? 60%. 60% for the final. So yeah, there's things like this call we're on just now. If the network began to become congested and packets started to get dropped because the congestion was so bad, then the call quality really starts to drop. You might find that some packets, they try and kind of make it up, so if one packet is received, the second one's dropped, the third one's received, you might be able to make up the middle one from what you've got in the other two. And some systems are able to do that, especially with compression, so they can decompress and go, right, if that was there and that's now here, then the middle one should have been here. So in that sense, there is a sense of intelligence, but once you start to drop a lot of packets, it really becomes noticeable on voice calls and on video especially. Once you start to drop a few packets, you start to get weird noises. Obviously the screen quality really drops. You might get things going out of sync. So voice calls, video calls, or if you're streaming Netflix or anything like that, or video conferencing like we're doing now, these kinds of traffic, kinds of network traffic, have to have some kind of priority over just normal, say, web surfing traffic or email traffic that can be a bit more or a bit less time sensitive. There are some things that if you're doing maybe internet banking, or if you're trying to do something online financially, they are probably time sensitive and they'll have greater needs than perhaps web traffic, standard web traffic. But the financial transactions won't be maybe as high a requirement as a video call or video traffic. So packets are buffered at the router, and they go into different queues, and they get into queues dependent on what their priority is. So the highest priority might be video and voice, so they get the preference if there's a queue. There might be a medium priority queue for things that are a bit more time sensitive, but are not as crucial as the likes of a video or voice traffic. And then you've got a low priority queue as well, and that'll be just for standard email traffic, web traffic, that kind of thing. So quality of service, it allows network administrators to decide what types of traffic they're going to prioritize when there's congestion. Remember, this is only when there's congestion. This doesn't happen all the time. This is only when there's congestion and there has to be a decision made over which packets are going to get the preference here. So quality of service is only needed when there is congestion on the line. There we go. So it's an ever increasing requirement in networks, thanks to voice transmissions, live video, which create higher expectations for quality delivery. So congestion can occur when multiple communication lines aggregate together on a single device. So it's perhaps these are all internal. This router here is the router that connects to the internet, and it's quite feasible that you've got quite high speed, maybe gigabit lines inside, and you've maybe only got, a slower, say 30 megabyte line out potentially, so you're going to have much more data concentrating here, waiting to get out onto the internet, because that is a much slower line. Think about it. See if they shut 2 lanes of the motorway. Think what the motorway goes like. It just queues right back, doesn't it? Even if they close 1 lane in the motorway, it queues right back. Especially when it's at a kind of busy time. This is the same kind of analogy. And so if you could prioritize certain people, you could jump them over the queue and get them there faster. So it says, these lines aggregate where there's a router, and then much of that data is placed on a fewer outbound interfaces or onto a slower interface, perhaps both. When the volume of traffic is greater than what could be transported across the network, the packets have to queue up or hold inside the router. But the router's only got a certain capacity, remember, of memory, so it can only hold them so far until it gets to a point where my memory queue is full. So what does it do once its memory queue is full? It has to drop packets, and it's that dropping of packets that causes the kind of outages and desynchronization on video calls, poor quality, and having the line just dropping altogether. So queuing packets causes delay because new packets can't be transmitted until previous packets have been processed. Once memory fills up, packets dropped. And one quality of service technique that can help is to classify data into multiple queues. And that's where we had a high, medium, and low priority queue. And it said it's important to note, and this will probably, when they say it's important to note, that'll probably come up as a question somewhere. It's important to note that a device should only implement quality of service when it's experiencing congestion. All right. So there are all sorts of things that can cause problems. Network bandwidth, that's the number of bits per second. So if you're aggregating, a large amount of lines onto a smaller network bandwidth, then you need to be aware of, if you've got fast lines, so gigabit lines going on to megabit or 1 megabit line, the network bandwidth is going to change. So there is going to be a queue there. Can you do with that queue? Can you live with that? Network congestion is going to be definitely a consequence of that. That's going to cause delay, because it's going to, if it's presented with more traffic than it can handle, it's going to cause congestion. The delay or latency refers to the time it takes for the packet to travel from the source to the destination. So that there might be a fixed delay, or it might be a variable delay depending on the traffic that's coming. If it's a fixed delay, you could probably live with it a bit more than you could with a variable delay. And the jitter is the variation of delay in the packets. So these are all terms that we've probably covered back in semester 1, semester 2, but it's just they're here again just to remind you about what these are and how they apply to quality of service. So if you didn't have any quality of service mechanisms in place, packets are just processed in the order in which they're received. So it's first come, first served. If congestion occurs, then once the memory is full, it just drops packets. And if there's no quality of service, you could be allowing non-time sensitive HTTP traffic going through, and time sensitive video and audio packets are going to get dropped. So it's not great. So when a router receives a digital audio stream for VoIP, it must compensate for the jitter that's encountered. The mechanism that handles that is the play out delay buffer. It must buffer the packets and then play them out in a steady stream. So rather than having, this is how they're received, there's a play out delay buffer and it makes them de-jittered. So they all come out on a regular, one after the other. The digital packets are then later, obviously, at the headset end, converted back to an analog audio stream. If the jitter is too large, then packets that are received out west of that buffer can be discarded, and that's when you get the dropouts or the weird kind of noises that you sometimes hear, especially on mobile phones and sometimes on audio calls. For losses as small as one packet, the thing I was talking about, a digital signal processor can interpolate what it thinks the audio should be. If the audio was here and then the next audio packet's here, it says, okay, the one that's missing must be around about here, and I'll guess. Doesn't always guess it right though. But when the jitter exceeds what the digital signal processor can handle, that's when you can hear the audio problems. But in a properly designed network, your voice packet loss should be 0. You shouldn't be losing any packets for voice. As soon as you lose one, it's starting to get a bit dodgy. Lose more than one, you're going to get kind of noise and interference. So network engineers use quality of service to classify voice packets for 0 loss. They are fast-tracked through. Voice and video obviously are going to place a greater demand on the network, and they are 2 of the main reasons that quality of service is here at all. The difference between voice and video traffic is voice traffic doesn't cause a lot of resources, it doesn't consume a lot of resources. It's quite a narrow bandwidth for voice, because you've only got a certain audio range. So it might be, it's only maybe taking the middle part. It's maybe only, I don't know, say 8 kilohertz up to 15 kilohertz or so. It's very, very narrow. So the packets tend to be smooth. They tend to be quite benign. There's no big spikes in it. They are drop sensitive, they are delay sensitive, and they will be delivered by UDP to help the throughput, and they should have priority. So the latency requirements, there shouldn't be any latency of, well, there should be any latency greater than 150, so less than 150 milliseconds. The jitter should be 30 milliseconds. The loss, ideally 0, but less than 1%. And the bandwidth, oh, there's the bandwidth there, 30 to 128. Okay, so not huge. Video is different. Now, if you think about when you're streaming video, if you're watching a film or something, there might be quite like some scenes where there's not a lot happening. And so one screen, if there's 50 screens a second, or however many it might be, 25 screens coming up a second, if it's quite a still picture, so if you imagine, it's quite a kind of static scene in a film, then because it's compressed, there's probably less data has to be sent, because there's very little change from one scene to the next scene in terms of the video screens. So you probably find that the packets needed to show that will drop. But as soon as you get an action scene again, so maybe there's a lot of kind of fight action, or there's maybe a lot of movement on the screen, then one screen to the other, there's a lot of change. And so the compression algorithm can't really do much about that. And so there's more data required for that. And so in that sense, video can be what's called bursty. Sometimes you get lots of packets, and then when there's a quiet part or a quiet scene, it might be, it might tail off, and then there's a lot of movement again, and that causes the video to go up and down, up and down, up and down, up and down, in terms of its, the amount of packets going through. So it's bursty, it's very greedy on the bandwidth. Again, it's drop sensitive, delay sensitive, and they're sent through UDP, but there's also some kind of priority has to be put there. The latency requirements 200 to 400 for video, so slightly less than voice. The jitter 30 to 50, very similar. The loss 0.1 to 1, so the loss is, it's a lot less. But you can see the bandwidth requirements are much, much higher. So you're talking 384 kilobits per second, or thereabouts. So in the early 2000s, predominant types of IP traffic were voice and data. There wasn't any kind of streaming video. We didn't have the bandwidth for it. Voice traffic had predictable bandwidths, it had known packet arrival times. It's easy to deal with. Data traffic is not real time, so it's got an unpredictable bandwidth need. But more increasingly, video traffic is the one that's becoming increasingly important to business, especially now. And it said by 2019, video traffic will represent 80% of all traffic. So we're already 2 years beyond that. So we're maybe looking at the way that's climbing. We're probably looking at 90% of all traffic on the backbone of the internet is going to be video. If you think about, even if you're scrolling through social media, how much of social media is video now? So it could well be right. So the type of demands that voice, video, and data are placing on the network are very different, and so quality of service is becoming increasingly important. So, like we said, voice traffic is predictable and smooth. It's, however, very sensitive to delay and drop packets. There is no reason to retransmit voice packets if they're lost, because if you retransmit them, that ship has sailed. You know what I mean? There's no point in retransmitting packets, so don't lose them in the first place. So for that reason, they must receive a higher priority. Cisco products use RTP for voice traffic, and the ports range from 16384 to 72727. So those ports are prioritized for voice traffic. It can tolerate a certain amount of latency and jitter, as we saw, 150 and 30, without any noticeable effects. But these are 150 and 30, and the voice packet loss should not exceed 1. Video is different. It's less resilient to loss, and there's a higher volume of data per packet. So you can see, different video frames. Depends on the traffic. So if it's a very still scene, there's less traffic. If it's a very busy scene, there'll be more traffic. And here's 33 milliseconds. You can see the contrast, the number of size and video packets every 33 milliseconds as compared with voice. So there's 20 milliseconds between those two. There's the voice samples, but there's video, and you can see the difference. It's much, much more bandwidth required. So yeah, if the video quality starts to degrade because packets are dropped, then the picture appears blurry or jagged or in slow motion. The audio will become unsynchronized. So video, like we said, it's bursty, it's greedy, it's drop sensitive, it's delay sensitive, and it's got a UDP priority. And those are the figures around that. Data. So most applications either use TCP or UDP. And unlike UDP, TCP does the error recovery. Now, you can't have error recovery on video or voice. It's just not possible, because if you were trying to resend a packet to put it all back in place, the voice conversation has moved on. So you wouldn't want a legacy voice packet coming back in a second later or 10 seconds later, because that's gone. So voice and video can't be TCP. So that's why they're UDP. But data is different. Just general data is different. It can be TCP or UDP. Data applications that have no tolerance for data loss, such as email and web, will use TCP to ensure packets will be resent in the event that they're lost. Some TCP, such as FTP, can be very greedy in terms of pulling down large parts of network capacity. And if you've ever downloaded using FTP, you can virtually hog up your whole router. So yeah, you've got to be careful with that. So you've got to be, either set it to be a certain amount or give priority for other things. Although data traffic is insensitive to drops and delays compared to voice and video, you still need to consider the quality of the user experience at the end of the day. You can't wait forever for a web page, because every other bit of traffic is getting prioritized, not web traffic. So you've got to think about, are things, in terms of data delay, is the thing that you're doing, is it interactive or is it non-interactive? If it's interactive, then you've got to then think, is it mission critical for your business or is it not mission critical? So interactive is something that you'd have to, chat back and forward, like, we're doing maybe on the chat facility. That's interactive. So is it mission critical? Well, Teams, yeah, it would be. So you would want to prioritize that. If it was just Skype chat or internet relay chat or something else, it's not mission critical, then applications could probably be left to having some kind of delay on it. If it's not interactive, perhaps sending an email, then is it mission critical? Yeah, for your email it would be. Well, okay, delay can vary greatly as long as the necessary minimum bandwidth is supplied. If it's not mission critical, then it gets left with whatever's left over after all voice, video, and other data applications are met. So it's basically saying voice and video are up here, other data is down here, but for your other data, try and classify it as well, and try and classify it into, is it interactive? Does it need to be back and forward? If so, give it a little bit more priority. Is it non-interactive, like an email? Probably give it less priority. And then you've got to decide, is it mission critical for your business or not? And then you can obviously prioritize them that way as well. There's a good video tutorial in the curriculum if you want to have a look at the chapter for chapter 6, and it talks about how the priority classification can work. But it's basically like a queue. So without quality of service, you look at first in, first out. So the first into the interface is the first one out of the interface, and that's basically no quality of service. Packets that come into the router will leave in the same order. Then we'll look at things like weighted fair queuing, and that's where you give different types of packets different priorities or different weights, and so they have different queues that they will go to. So we'll look at weighted fair queuing over the next few slides, and class-based weighted fair queuing, and we'll look at low latency queuing as well. Okay. So the quality of service that's employed by the network admin becomes active only when there's congestion on the link. If there's no congestion, then there's no need for it. If you're using quality of service, it will slow down your network slightly, because think what the router has to do. It has to look at all the packets and say, right, who do you belong to? Oh, you're a video packet, right, you go there. What are you? You're a voice packet, right, you go there. What are you? Or your data. So by simple fact that it has to look at every packet, it's going to slow down your network. So you don't need quality of service unless you've got congestion happening. So once you do have congestion happening and you've got queuing, then quality of service kicks in. And we'll look at which one of these will kick in. And we'll look at 4 different types. So the first in, first out, it's known as, hold on a second, see if I can stop that. It's a bit of a pest, that's it. So first in, first out, it's known as first served queuing. The router just buffers the packets, sends them out in the order that they arrived. No concept of priority, doesn't understand classes of packet, makes no decision about packet priority. There's one queue, everybody's treated equally. When first in, first out is used, important or time-sensitive traffic can be dropped if congestion occurs. When there's no other queuing strategies configured, first in, first out is used on serial interfaces. So it's okay if you've got a large link that's got little delay and minimal congestion. If your link has very little congestion, first in, first out might be the only queuing that you need to use. But you can see straight away where problems would start to build up. If there's more data coming in here than can be sent out, then you start getting a queue, and if you start filling up your buffer and you start getting congestion, voice and video might suffer. So weighted fair queuing is an automated scheduling method. Basically, it provides fair bandwidth to all different types of network traffic. And it applies priority or different weights to different identified bits of traffic, and it classifies them into different flows. And it then determines how much bandwidth each flow is allowed to have. So it will schedule interactive traffic to the front of a queue to reduce the response time, and then it shares the remaining bandwidth among the other high bandwidth flows. And you can see it classifies traffic into different flows: high, normal, medium, and low. And you can see packets going out that way. In the high priority go out first, then the medium, then the normal, then the low. And it classifies them based on the packet header, including the source destination, IP addresses, MAC addresses, port numbers, protocols, the type of service values, all these kind of things. Does it automatically based on what it thinks is best. There's also a class-based weighted fair queuing, which extends that standard functionality to provide support for user-defined classes. So you can define on your network, right, well, I want to add some other things that are important to my network. And so you've got different priorities that you can define. And you can define them based on match criteria, including maybe the protocol that's using. You can use it via access control lists that the interface they've come in on. So when a class has been defined, according to its match criteria, you can assign it characteristics. You can assign it some bandwidth, weight, maximum packet limit, and the bandwidth assigned to a class is a guaranteed bandwidth that class will get when congestion occurs. So packets that match the criteria for a class constitute the traffic for that class, and you can see obviously the priority that goes there. You can see that there, traffic that's number 4 goes into class 1, goes into weighted fair queue, it goes out first, then class 2, then class 3 traffic. So you can be a bit more in control rather than relying on the automatic weighted fair queuing. The class-based, you decide the classes and you decide the bandwidth that's allocated to them based on your network needs. So you've got a bit more control over it as a network admin. You've also got low latency queuing, and that brings along with it strict priority queuing, which is PQ, priority queuing, to the class-based weighted fair queue. What that allows is it reduces the amount of jitter in voice conversations because the queue is a lot quicker. It allows delay-sensitive data, such as voice, to be sent before packets that are in other queues. So you can see you've got classes here, but you've got a priority queue. And so, for example, if voice packets are coming in, you can see these 1 and 2 have been assigned as being class 3. Number 3 has been assigned as class 2. That voice packet goes up class priority. It gets straight to the front of the queue. And you've got, again, and there's number 4 goes into class 1. There's another voice packet. So that voice packet again goes out even before number 4 does. So it just allows things that are really, really delay sensitive to be pushed right to the front of the queue, and then other things can fall in behind that. Without that low latency queuing, your class-based still provides your weighted fair queuing on defined classes, but it doesn't have strict priority for real-time traffic. So you would probably want your voice and video to be through the priority queue, and then everything else to be through these classes. And that might be financial transactions are in here, and anything else that's maybe interactive here, and then everything else is under class 3. Okay. Now, the quality of service mechanisms, these identify basically how you implement these in reality. So before we move on, is everything okay with the quality of service idea? It's all about different mechanisms, different ways to ensure packets have priority. You can see clearly that voice and video need to be pushed to the front of the queue, because you can't resend the data. You can't drop a packet and then get it back later on. It's time sensitive. Once it's been sent, the ship has sailed. So you've got to do everything to try and get that traffic through. And there's different ways of doing it. Obviously, first in, first out is what you would have normally. If congestion occurs, you've got some kind of weighted fair queue, and then you can maybe some kind of class-based weighted fair queue, and then you've got class-based weighted fair queue with a kind of fast pass for voice and video, which is the LLQ. Is that okay before we move on? Yeah. Do anybody want to ask anything on that at all? No? Okay, I'll move on. So again, in the curriculum, it's well worth having a look at the video tutorial that's here. Basically, it's quality of service across a network, and it's how to get that idea. How do we actually achieve this? There are different models. So you can see here, here's your quality of service aware node. You've got a network here in the cloud, and then you've got your quality of service aware node on the other end. Effectively, what you should have between these two quality of service aware nodes is end-to-end signaling. So that, yeah, although they're going through here, it's almost like a tunnel idea, that they have end-to-end kind of signaling. So this is an integrated services example. Because if you think about what the main floor of this is, packets are delivered on a best effort basis. If they're going UDP, if they don't get there, they'll just drop. So it's still best effort. And best effort is not really an implementation of quality of service. You want to ensure that the packets are going to get there. So the integrated services model, sometimes shortened to IntServ model, it provides a high degree of quality of service to IP packets, and it tries to provide guaranteed delivery. Uses a signaling process known as RSVP, or Resource Reservation Protocol. It's basically to try and allow for packets to be assured that they're going to get to their destination. It's guaranteed delivery. The differentiated services model, DiffServ model, is a different model. We'll see it later. It's highly scalable, and it works with flexible implementations of quality of service. And it works off manually configured traffic classes, which need to be configured on routers, whereas the IntServ is more a kind of automatic kind of one. So how can quality of service be implemented in a network? Well, there's 3 models for quality of service. Best effort, which is not really an implementation of quality of service, because quality of service, it's not explicitly configured. Maybe use it when quality of service is not really required, but you're either looking at serve integrated services or differentiated services to make sure that quality of service will be, will happen right across the network. So the integrated services, the int serve, it gives you high quality of service type E packets, guaranteed delivery. It's got a different signaling process to signal to the network that these require special quality of service for a period, and that bandwidth should be reserved for these packets. But intserve can severely limit the scalability of a network. So if you want a bit more control over it, you're probably better with differentiated services. They again provide high scalability and flexibility in implementing it. The network devices recognize the traffic classes and will provide different levels of quality of service to the different traffic classes, but you need to tell it what your traffic classes are. So you would need to define it for your network. So intserve provides the highest guarantee, but it's resource intensive. Diffserve, less resource intensive, but more scalable. So balance it
out. Hi, Ian. Can I ask one question?
Yeah.
Is there any questions in an exam related to QoS? It's very dry.
There probably will be. I think if you just, the important thing to know is the main concepts. The main concepts are understand what quality of service is for, why it's there, and what it's going to be used for. In terms of, I don't think there's any quality of service in the practical. I don't think. But it's very, very important to understand why it's there. It's one of these ones where you can obviously see what can happen if you start dropping voice packets and video packets. It's game over, really. So you need to have a way of ensuring that these things are going to get through. And by using one of the methods of quality of service, that's going to ensure that happens. But I think if you just remember why it's there, and knowing that a network has got to be able to differentiate between different packets and offer them different bandwidths and offer them different queues in order to help them on their way, that kind of understanding of it, and some of the terminology and some of the acronyms that are in there, you probably will be asked about in the final. So it's worth reading through the chapter just to pick up some of that, but just know on a basic level that quality of service, what it's for, why it's there, and how it's achieved, essentially. So I haven't got many slides to go, so we're nearly at the end of it, and I do appreciate that it's been a long chapter, and it is quite dry because it's very, very difficult to implement in reality. But yeah, stick with it. We're nearly at the end. So, best effort model. Remember back to the basic design of the internet, which is still applicable today. Packets are delivered on a best effort. Packets are delivered on a best effort delivery model, and there's no guarantees. The best effort model treats all packets the same way. So without quality of service, the network can't tell the difference between packets. So a voice call would be treated with the same, priority as an email with a digital photograph attached. So the best effort model, if you think about it, is like sending a letter using the standard postal service. Stick your letter in an envelope, stick a stamp on it, put it in a post box, you hope it gets here. Quality of service needs more than that, okay? So integrated services, what we're going to look at is a couple of examples of integrated services, one of differentiated services, and then that's it. So The needs of real-time applications, remote video, multimedia conferencing, all of these sort of things led to the development of the IntServe architecture model. And it's a way to deliver end-to-end quality of service by explicitly managing network resources to provide quality of service for that stream. It's resource reservation. Basically, it says, right, I need this amount of bandwidth, go and reserve that for me, and it can do that. It's a bit like a connection-orientated approach in which, yes, you're going through the backbone of the internet, you're going through the cloud, but it's as if you've got an end-to-end connection between the two. So that's IntServe. It has to request the specific kind of service from the network before it sends the data because it's connection orientated. The connection is then set up, the resource reservation protocol kicks in, reserves the resource, reserves the amount of bandwidth it needs, then the transmission can begin. If it doesn't get all the network devices along the path to reserve the necessary bandwidth, the transmission doesn't even begin. Okay, so it has to get every single network device to say, yep, I agree to reserve that bandwidth for you. I will reserve that bandwidth for you. Boom, we'll go right across. Okay, if that doesn't happen, if that bandwidth isn't opened and reserved, it won't start. No data is sent. So that's integrated services. Okay, differentiated services, slightly different. It's more simple, but it's more scalable. It does give you quality service guarantees. It does give you low latency for voice and video traffic. It overcomes the limitations of the best effort, which is no quality service at all, really, and the limitation of IntServe, in which case, you have to open up the line all the way before data is sent. It's an almost guaranteed quality of service, not guaranteed fully, like IntServe is. It's almost guaranteed, probably the best of both. It's cost effective though, and it's scalable, and it works. It's not an end-to-end strategy because it can't enforce guarantees, but it's more scalable. It's just a bit more realistic, isn't it? So you can see the figure on the left, forwards traffic to a router, the router classifies it, it then throws it across the network, and you can see essentially you've got quality of service going across. It does enforce it and applies it on a hop by hop basis rather than opening up the line right through, but that's where you've got the flexibility and the scalability in there. It divides network traffic into classes. Each class can then be assigned a different level of service. There is a video tutorial as well, if you want to have a look at that, and it's probably a bit more interactive, but it shows the packets coming in, then being classified and marked, then there's congestion avoidance, then there's congestion management, and then there's scheduling and shaping the data, and then it goes out through the outside interface. So classifying and marking it is the process of marking it into the different packets are marked based on what type of traffic they are. Then there's congestion avoidance tools. And some packets to prevent, if there's congestion coming, you can see it start to build. Some traffic might be selectively dropped, it might be delayed, or it might be just remarked and be told to be resent. Forget that just now, just resend that later time. So during congestion, managed traffic is queued, and then obviously based on their fair queue, they go out in a different order. Okay. Packet loss is usually the result of congestion, and most TCP applications will slow down the speed of transmission because TCP will automatically adjust to network congestion. Some applications don't use TCP, like voice and video, they're UDP, and so they can't handle drops. So what can we do to prevent packet loss? Increase the link capacity, if it's possible to do that. Guarantee enough bandwidth, and increase your buffer space to accommodate bursts of traffic, whether you use some kind of fair queue to do that. and prevent congestion by dropping packets that are of a lower priority before congestion occurs. And there's a weighted random LA detection facility that can do that. It says, oh, wait a minute, this is going to start getting backed up in a minute. You're not coming in because you're not important traffic. Wait till that important traffic's gone, then you can come in. Okay, so it's a bit like policing, really, isn't it? So there are three categories of tools. There's tools for classifying and marking. There's tools for congestion avoidance, and there's tools for congestion management. And obviously, classification and marking is all about identifying the packets and what they are and how important they are. There's ones about selective dropping, so you can decide which ones are not important and which ones still are important if congestion's about to occur. And then obviously it's all about queuing and putting things to the front of the queue. Okay, so this is just continuing on from that. So you could say, well, different types of Ethernet packets might have a different class. Wi-Fi might have a lower class. You know, different ways of looking at it. But usually it's a value that's added to the header that determines what the packet type. So you can see here, there's your marking at layer 2. So there's 3 bits used for user priority there. And depending on the value in here, that's the priority at layer 2. So that will be priority going around marking it at layer 2. Yeah. Do ISPs offer a way of bypassing the quality service? Possibly. There might be ways that you can do it through, I'm not sure if there's ways that you can do it through some kind of tunneling. Yeah, you could probably do it if you had a VPN or something like that. You might be able to bypass it. So yeah, possibly. Marking at layer 3 happens at layer 4 through type of service, through IPv6 traffic class. And depending on the value in those headers, you can see that there is different priorities: low drop, medium drop, high drop, depending on where they are. There's also best effort. That's the default for all IP packets. There's ones that say expedited forwarding, and that's the ones that should be used to mark voice packets. And there's assured forwarding. So they, you know, it's just different ways. If you wanted to use best effort, the value for that would be 0 in that field. If you wanted to use expedited forwarding, the value would be 46. If you wanted to use assured forwarding, then you would look at this table and decide which one you want, and basically designate it whatever way you want. Where should the markings occur? As close to the source as possible. Traffic should be classified and marked as close to the source as possible, so it allows to traverse the network properly. You might find that traffic has to get remarked, depending on where it gets to. But usually there will be endpoints, so that, like, for an IP call, the endpoint would be the telephone, the VoIP telephone, for example. The congestion avoidance mechanisms, it monitors traffic to anticipate and to try and avoid congestion before bottlenecks occur. Congestion avoidance is achieved through dropping packets, basically. So it's just a matter of saying, well, congestion is going to happen unless I do something about it, and doing something about it would be dropping packets. And there's tools that monitor the average depth of the queue. And when the queue fills up to the maximum threshold, then a small percentage of packets are dropped. When the maximum threshold is passed, all packets are dropped. So you can see, yeah, once the queue is empty, nothing gets dropped. once a threshold appears, some of them get dropped, but if it does get full, if it's full, it's full, can't do anything. So you have to drop them all. Cisco does have a weighted random early detection facility to try and basically allow a congestion avoidance technique to allow preferential treatment of which packets will get dropped. So some things that use TCP application performance, because you can slow down the TCP window, because TCP can re-request packets, they're probably the ones that would get dropped. There's no congestion avoidance for UDP, such as voice, because you can't resend UDP. You can resend TCP, so that's why they can get dropped. The shaping and policing, we've kind of covered this. I'll just quickly kind of go through these. Basically, if you've got a committed traffic rate that you've paid for your line, you probably don't want to go over that. So you can basically use traffic shaping. In other words, retain excess packets in a queue and then schedule them for later transmission over time so that your traffic will stay at a constant output. It won't jump up, down, up, down, up, down, up, down, and then go over the committed information rate. If you go over your committed information rate, packets are going to get dropped anyway. So at least if you can schedule them, retain them and schedule them over time, you can see you can smooth it out. You can see obviously the smooth shaping. Policing is commonly implemented. Policing will either drop packets or it will remark them. So remark them means reclassify them to be something else. And that will get your traffic down below your committed information rate as well. It's often applied to inbound traffic coming into a router, prevents it getting it back out. Okay, quite a big chapter there, quite a dry chapter, as Mohammed had said. But I hope you get the idea that not every packet is treated the same. Not every packet can be treated the same. There has to be some kind of difference in there. There has to be something that allows for, better throughput of voice and video to the detriment of just general surfing traffic. There's also got to be ways that if congestion is starting to build up, that you can maybe try and prevent it by trying to hold back or just push back packets just for a little while to allow the congestion just to die down a bit. Remember, quality of service doesn't really kick in until there is congestion. So, as long as the packets are getting through, it's fine. It's when the packets start to slow down and there's a bit of congestion that starts to all back up that quality of service needs to kick in. So just bear that all in mind. Obviously try and pick up on some of the kind of keywords that are through there that will probably be important for the assessment. So you're probably going to be asked maybe about 5 or 6 questions based on this area. So as long as you get a general idea of what quality of service is about, what the techniques are, what some of the different queuing mechanisms are, you should be absolutely fine. It's known, it's known all about how it works and how it can operate. Okay, is everybody okay? Does anybody want to ask anything on that, or have I just kind of bored you into submission with that one?
Ian, just one question again.
Yeah.
Just related to the CNC certification stuff. So far, whatever the content has been delivered to us, is that enough to go for the CCNA exam, or we need to prepare more stuff for CCNA? Right.
You need to prepare a little bit more stuff. In your first year, you did semesters 1 and 2. No, in fact, you did semester 1. You did networking technology. You did semester 2, I presume with John, and you did some of semester 3. So there are a few chapters from semester 3 that you didn't cover. So what I can do is I will create you a semester 3 course, just so you can go through the chapters that you didn't cover. I think there's maybe about 4 chapters that weren't covered. Other than that, other than those 4 chapters in semester 3, yes, you have the entire knowledge that you need for your CCNA, because you've gone through 1 in your first year, you've gone through 2 and half a 3, say, in your second year, and you've gone through 4 with me. So it's only that little bit, maybe 4 chapters out of semester 3 that you haven't covered with John, that you would need to sort of read through. Other than that, yeah, you could sit at CCNA. So I'm going to keep this semester open, even though once you've finished the final, I'm going to keep the semester open for semester 4, because you've got chapters 7 and 8 in there, and 7 and 8 is, of course, the ones that are the revision chapters for the CCNA. So you can go through those chapters and just get the kind of revision. There's also CCNA practice exams in there as well, just to see if you're at the right kind of level. I think there's 2 CCNA practice assessments that if you're passing them, then, you know, with 70 or more, you're probably going to be okay for the CCNA as well. Is that okay?
Thank you, Dad. Thank you.
All right, sorry. Liam, when can you take what, the CCNA, or I'm just going to pull up our schedule. The final, you're probably looking at sometime in June. I think you would probably be ready around about there. Let me just, where are we, teams? Just give me a wee second, I'll pull up our schedule and I'll see where we're at.
Ian, just a quick question. By any chance, you know, the practical test, I'm guessing that's going to be on Packet Tracer?
Yeah, it's already there, that's fine. It's on assignments.
Okay,
Remember I went
so,
over it last week?
yeah. So the Packet Tracer and the final test, the final exam, basically, that's what's left?
Yeah, that's what's left for us. I'm just going to pull up the schedule so you can see exactly what we need to do. Here we are. Right. So we are, where are we now? Oh, these have all gone down by 1, so I should have pulled that. Right, that's fine. No, that's fine. Right, so this is us today. We are here. So we're at the 4th of May, and we were going to cover SNMP from chapter 5 and chapter 6. That's what we did. So we've finished now. Under the work task to be completed by a student, I've said finish chapter 5 today and finish chapter 6 by next week. And that should be all your chapters done. Now, next week, what we're going to do is we are going to do a revision, just a quick revision of everything. Obviously, a top high level. I'm not going to get into nitty gritty of a lot of things. It's just really talking about concepts of the things that we've spoken about. So perhaps about half an hour just to regroup, refresh our memories. Yeah, what did we do? Let's think back, and it gives you a chance to ask me anything you want to ask me about anything that we've covered so far. I will also next week start the tutorial that goes towards completing the Packet Tracer assessment. Now, if you've started it, it's absolutely fine. If you finished it, even better. But what I want to do is for the people that are maybe thinking, oh my God, I don't even know where to begin. How do you even start this? I want you to just start from, you know, not quite scratch, but start from the beginning and say, right, okay, it's asking you to do this. What does that mean? What do you need to do? What commands do you need to use to do that? And just take you through it step by step, and just, you know, show you where it's come from, show you what the commands are, and, you know, and I'll do that for parts 1 to 4, because that'll probably take quite a bit of time, and there'll be a lot of info in there. Then what I'll do the week after is we'll have a look at your practice final results, and we'll get you to do a practice final sometime in that week. I'll do a revision based on your practice final results, just to see where people were going wrong and what questions they were getting wrong, just in case there's any common threads in there of things that you hadn't quite picked up. Then I'm going to do the completion of the tutorial towards the packet tracer assessment. So that'll be parts 4 to 8 or something, or 4 to 7. So I'll just say parts 1 to 4, and this will be parts, I think it's 5 to 7. So I'll take that bit out because you won't have done the packet tracer yet. Then on the 25th, I'll do a final revision based on your practice final, and then you'll do your final exam. Then the packet tracer is also due on that date. So here are the next stages that you should be doing. You should, by today, have finished chapters 1 to 5, if you haven't done so already. By next week, I want you to have done chapter 6 as well. I will go over a whole revision of everything, just to refresh your memory, and I will do a tutorial showing you the first half of the packet tracer assessment. Then by the time I see you on the 18th, I want you to have done the practice final. Practice final, yeah, is on NetAcad. And just to give you an idea of how you're looking, I will also do the rest of the tutorial based on the packet tracer assessment, parts 5 to 7. And then the week after that, we will do more revision. This would be purely based on how people have done in the practice final, and it will address any kind of common threads that you might have, or where people have gone wrong, and just gives us a chance just to, again, just regroup, talk about that stuff, ask any questions, and then you'll do the final exam at that time. The week after, which will be the last week, we've got the final exam reset, if anybody requires it. Yes, it's CN practice final exam, yeah. I don't know if it's actually active. I can make it active for you just now. Just in case anybody wants to get a head start, but all the chapters are up and running. I'm just going to set up the practice final if anybody is ahead of the game and wants to have a look. Again, don't do it till you've done all chapter exams, all 6. Does anybody, just while I'm setting this up, does anybody have any questions at all? Just while you're all here, I'll just take an attendance. Okay. So what I'll do is I'll just go in and create an activation, and I'll show you the things that you need to do. CN practice final. CN's connecting networks. I'll make it available until the 5th. Okay, that's it set up. So what you should have done by this point is obviously Chapter 1 exam, Chapter 2 exam, Chapter 3 exam, Chapter 4 exam, Chapter 5 exam. You don't need to do that packet tracer. You can if you want, pure up to you, you don't have to. Chapter 5 exam, Chapter 6 exam by next week. So this is the one I want you to do by this week. This is the one I want you to do by next week. Remember, Chapter 7 and Chapter 8 are, it's just terms and concepts practice. It's really just a whole kind of revision stuff. We don't need to do it. The practice exam, CN practice final exam, that's the one I want you to do by 2 weeks' time. And of course, the final exam is the one we're going to do 3 weeks' time, is it? And that's, so it's this one exam essentially, and the practical that's inside Teams are the two things that I need to be able to make sure you've passed to be able to put you through for a pass for this unit. I'll just go back to Teams again, just to see if everyone is okay with the assignment. See if everybody's even had a chance to look at it, so you know it's there. There's so many assignments. Here we go. So it's called Internet Working Technology Practical Skills Assessment. Nobody's handed it in yet, which is no surprise, because obviously we're going to go through some tutorials of it next week and the week after. So wouldn't worry about that. Yep, a lot of people have viewed it, so certainly. Yep, perfect. Okay. So we will cover
Ian,
that.
sorry. What was that? Did you just say? A lot of people have viewed it.
Viewed it means just people have gone in and had a look.
At the the practical assessment. Okay, that's fine.
Yeah. That's fine. I mean, it's due date's not for a while yet, so but I just wanted to make sure people knew where it was. That's the important thing. So let's just go back quickly to the schedule then. So the schedule this week, we're at the 4th of May. Now this is on the files area of Internet Working Technology. You can pick up any point. We are on 4th of May. I want you to do Chapter 5 at least by this week. I'm going to do a revision and some tutorial towards the packet tracer assessment, half of it. And I want you to have done Chapter 6 by next week. I'm going to finish the tutorial on the packet tracer assessment the week after that. And I want you to have done the practice final by that point. The week after that, I will do any last minute revision based on what happened in the practice final, and you'll do your final exam that day on the 25th. Okay, so we'll probably meet up at 10, do a quick revision, half an hour, gives you a chance to ask any last minute questions, and then you can go on and do the final exam from that point on. That's also the day that the packet tracer is due in. The following week is when the final exam reset will take place. So if anybody doesn't pass, which I'm hoping everybody is going to pass final exam first time, but in case there's any issues, we've got a reset date week after. And I've said the rest of the time until the end of term, I'm going to set up a semester 3 for you, and that will allow you to complete all the CCNA semesters in full. So it allows you to do your CCNA. Probably, I would give yourself a lot of time, obviously, to study that. I would say 2 weeks constant study purely on the CCNA, at least, to be able to have a good chance of doing the exam. So you'd probably be looking at about the end of June, realistically, before you should be looking at booking it. Remember as well, if you pass the final exam, first attempt with 70% or more, you get a discount voucher for the CCNA, which I think is 58%. off. So it's a fair amount of money. Okay, but that's optional. That you don't need to do that in order to pass into networking technology. To pass into networking technology, you just need to pass the final, and you just need to pass the packet tracer. That's it. Is that okay? I'm just going to stop recording now.
Thank you.